we continue our discussion on ordered topology next with this definition. So as usual, let X be an ordered set with the ordered relation this less than some ordered relation. And let us also not forget that X has at least 2 points, and let A be a point in X, then this point A determines 4 subsets of X called the rays determined by A, and those subsets are these: A comma plus infinity open, that is the set of all points X in X which are greater than A. Minus infinity comma A open, this is the set of all points X in X such that X is less than A, and the closed versions of these two rays. This one is the set of all points X such that X is greater than or equal to A, and this one is the set of all points X in X such that X is less than or equal to A. The first two types of rays are called open rays. That means this type of rays are open rays, and this other one, they are also called open rays. And the last two types are called closed rays. Now the word open suggests that this should be open in the ordered topology. Actually that's the case. Let us see how. Say we focus on the ray A comma plus infinity open ray, and we want to show that it's an open set in the ordered topology. Now we are going to look at two cases. The first case is when our space X has a largest element B0. In that case, obviously this is the set of all points in the space which are greater than A, because there is now a largest element B0. So all those points will be less than or equal to B0 automatically. So this open ray becomes this interval, and we already know that this is itself an open set in the ordered topology. In fact, it's a basis element for the ordered topology on X, and that's why it's open. And in the other case, X will have no largest element. So in this second case, X has no largest element, and in this case you can easily check that your ray equals this union. The union of all ordinary open intervals A comma X, where X belongs to X and A is less than X. It's not a very difficult thing to verify. For example, okay, what will you do if you have to prove that this equality is true? You would have to show that each set is a subset of the other. Let us first consider an open interval of this type. Say you take a point y in A comma X. Then what does y satisfy? Y satisfies two inequalities. Y is greater than A and y is less than X. You focus on the fact that y is greater than A. Because y is greater than A, by definition y belongs to this ray. So any element in this open interval is here. So this is the subset of this, but that is true for any such X. So all these open intervals are subsets of this, and so their union is also a subset of this. Conversely, you take any element here, say Z, then what does Z satisfy? Z is greater than A. Okay. Now you use the fact that X has no largest element. So Z in particular cannot be the largest element of X. X has none. So there will be thus a larger element than Z. Let us call it beta, say. Okay. So now you have these two inequalities. A is less than Z and Z is less than beta. But that means that Z lies in the ordinary open interval A comma beta. But that open interval is one of these open intervals. Why? Because beta is greater than A. Where are we getting this from? That is because beta is greater than Z and Z is greater than A, and our relation greater than that, this ordered relation, is transitive. So beta is greater than X. So that's why you find that your chosen element Z is in some open interval here. So obviously it's in this union. So that way this is also a subset of this. So that's how they are equal. But then what does this tell us? It tells us that we have realized this ray as a union of open intervals, and these open intervals are open in the order topology on X. In fact, they are basis elements. So any union of these open sets is open. So that's how in this case also this is open. Similarly, this other type of open rays -infinity comma a, all of them are open as well. And to show this, you can proceed similarly, exactly similarly. Now the next thing is this. These open rays form a sub-basis for the order topology on X. This is the next thing we have to show. So to prove that claim, first of all, let us call the collection of all open rays S. Let's give it a name. And then the first thing we note about this collection is this. If you take the union of all the elements of S, then you get X. This is the first condition. Actually, it's the only condition for a collection to be a sub-basis for some topology on a set. We, however, do not just want some topology. We are claiming that S is a sub-basis for the order topology on X. I leave the verification of this to you. Okay, you go through all the details of showing that this is equal to this. One containment is obvious. You take any element A in S. What is A after all? A is an open ray, and an open ray, for example this one, is by definition after all it's a subset of X. So that means each A here is a subset of X. So their union is automatically a subset of X. You have to prove the reverse inclusion, that X is also a subset of this union. For that, you just have to show that if you take any point in X, that point has to belong to at least one open ray, either of this type or of the other type. So that part is left to you. But next we come to the more important part. The topology generated by this subbasis should match the order topology on X. How do we do that? Let's see. So we proceed like this. For convenience, we are going to name the topologies. Let tau be the order topology on X. Now this is something we have seen just now, that each open ray is open in X, is an open set in X. This means that any element of S is in tau, or in other words, S is contained in tau. S is a subcollection of tau. And that is why if tau prime is the topology generated by this subbasis S, then tau prime will be itself contained in tau. Why? Well, because S is contained in tau, so if you take finitely many elements of S, after all they are in the topology tau, so their intersection will also be inside tau as an element. That is because tau is the topology. So all finite intersections of elements of S are inside tau. And then you take arbitrary unions of those finite intersections. Any such union will also be in tau, again because tau is the topology. And that is why arbitrary unions of finite intersections of elements of S are inside tau. But these arbitrary unions of finite intersections of elements of S are precisely the elements of tau prime. That's how we generate a topology from a subbasis. If you only consider the collection of finite intersections of elements of S, you get a basis. And then when you take arbitrary unions of those basis elements, you get a topology. So that way tau prime is contained in tau. But we want the reverse inclusion as well. Now to prove the reverse inclusion that tau is also contained in tau prime, we aim to show that any basis element in tau is in tau prime. What are the basis elements of the order topology tau? They are ordinary open intervals of the form a comma b, or half open intervals of this form a naught comma b if x has the smallest element a naught, or means if this is there, this type of intervals are also going to be considered. So I should rather say and also intervals of this type if x has a largest element b naught. Alright. Suppose x has the smallest element a naught, and then you consider a basis element of tau of this form. Okay, so on one side you have constantly a naught, on the other side there is something b which is greater than a naught, that's understood. But note that this is nothing but this open ray minus infinity comma b, and this is already an element in S. And being an element in S means what? Being an element in S in particular means that it is also an element in tau prime, the topology that the subbasis S generates. So this type of intervals, if they exist in our space X, are actually in tau prime. Alright. What about this type of intervals if X, they exist if X has a largest element. Say X has the largest element b naught, and we consider some such interval where the right hand side is, the right end is b naught. The left end is something, some element of X which is a, that is less than b naught. Now this is just this ray a comma plus infinity. So this is also in S, and as a result it's in tau prime. So we have shown that these two types of basis elements for the order topology, if they exist, then they are inside tau prime. Alright, and now we are going to consider the general means the easy type of basis element, which is an ordinary open interval. To consider an ordinary open interval in X, we take two elements a and b in X such that a is less than b, and then we consider this a comma b. It's easy, almost trivial to check that this is equal to this intersection of two open rays minus infinity comma b and a comma plus infinity, and they being open rays are elements in S. And this is the finite intersection. In fact, it's the intersection of two elements in S. So it should be in particular in the topology tau prime generated by S, because the elements in tau prime are arbitrary unions of finite intersections of elements of S. So in particular, any finite intersection of elements of S should itself also be inside tau prime. So that's how this belongs to tau prime. And previously also we saw that the other two types of basis elements for the order topology, if they exist, any such basis element is inside tau prime as an element. So we can now claim means we can now conclude. So any basis element for the order topology tau is in tau prime. But then tau itself is contained in tau prime. Why? Because an arbitrary element in tau is an arbitrary union of such basis elements. If all the basis elements are inside tau prime, since tau prime is a topology, so any arbitrary union of such elements will automatically be in tau prime. So that's how we have the reverse inclusion as well, and that's how we have proved that this topology which is generated by the subbasis S is nothing but the order topology on X.